Alright, ladies and gentlemen, this is our forces practice test video in which I only go over the questions here, numbers 1 through 29, on our practice exam for Tuesday's upcoming test on forces. Here we're just going to look at Newton's 3 laws of motion as well as a few weight problems and friction problems. Okay. Alright, so these first 3 problems deal with Newton's first law of inertia, in which we relate mass and inertia together. And if you're going to notice, the first 3 problems, 1, 2, and 3, are pretty simple and straightforward. They typically ask about lowest or greatest amount of inertia, and if you know inertia is related to mass directly, increase inertia, you increase the mass. And number 1 asks for greatest increase. So if you want to produce the greatest increase in inertia, you just increase the mass of the object. So number 1 is choice A. Number 2, again, which object has the greatest inertia, so we're looking for just the greatest mass value, and that's choice D. Doesn't matter if it's in motion or not, we're just only looking at the mass. Speed has nothing to do with it. And number 3, again, which has the greatest inertia, regardless of speed, choice D is also our answer because it has the greatest mass out of these 4 choices. Alright, now numbers 4 and 5. Alright, number 4 deals with Newton's second law, F equals ma. Here we're talking about 2 objects, one 4 kilograms and the other 2 kilograms. And they're being pushed with the same force. The 4 kilogram object gets an acceleration of 3 meters per second squared. Now, based on Newton's second law, the smaller object should experience a greater acceleration. Mass and acceleration, if they experience the same force, should be an indirect relationship. One goes up, the other goes down. So if 4 kilograms gets 3 meters per second squared, a 2 kilogram object should experience a greater acceleration, 6 meters per second squared. You can also use the equation F equals ma and solve for it. You get 12 newtons for the first object. Carry that over to the second object and you should get A is equal to 6 meters per second squared. Okay. Number 5, what is the acceleration due to gravity at a location where 15 kilogram mass weighs 45 newtons? We're looking for G. We got M is equal to 15 kilograms, and we got 45 newtons as our weight F of G, force of gravity. So you plug it in, F of G equals M times G. 45 newtons equals 15 kilograms, solve for G, and we should get 3 meters per second squared. We're used to seeing 9.81, but that's because that number is only valid on Earth. Here in this problem, we're looking at a different location outside of Earth. Okay. Alright, so I've seen a couple of you have already struggled with number 6. Here we're looking for the diagram that produces the greatest magnitude of acceleration. So if we want to get great acceleration, we want a great net force. And so we can look at each of our 4 choices, see which ones already produce 0 newtons as our net force, so you could cross them off. And we're looking at choices B and D because all of those forces are balanced, therefore our F net is 0. Now we're looking at A and C. I'm going to draw each of them out right here. So we can see that A has 2 unbalanced forces and C has 3 forces. 2 of them, top and bottom, are balanced, so you could cross them off, and all we're left is that one to the right. That's the only unbalanced force there. So when you actually figure this out numerically, you get A, choice A gets a F net of radical 2, and then choice C has a F net of just 1 newton. And you could say that choice A is our answer. The greater net force, greater acceleration. What's next? Number 7. Alright, so we're looking for what is the magnitude of the object's acceleration given these forces and the mass. So here, let's start with a free body diagram. We have here 15 kilograms in the center with 25 newtons pointing up and 35 newtons pointing down. Because they're different amounts, we have an unbalanced force. So 25 and 35 acting opposite, we take the difference to find our net force, and our net force here is 10 newtons. Plug it into F net equals ma. Figure out what is our acceleration, because a net force, once again, causes the acceleration. So 10 newtons equals 15 kilograms, and A is equal to 0.67 meters per second squared. Yeah. Next is number 8. Here we are encountering our old nemesis, motion graphs. Okay, so we're looking for the graphs that best represent the motion of an object not in equilibrium. So that means we're looking for acceleration. And if we look at each of our choices, A, B, C, and D, A shows the object at rest. B, changing speed over time, shows acceleration. C is a constant speed. And D is also a constant speed. In the background, I'm watching Zootopia, and it's one of my favorite Disney movies ever. Alright. So choice B is our answer. Now number 9. Here we're looking once again at motion graphs, looking where the net force is 0. So if we have a net force of 0, that means we are in equilibrium. And so we have two scenarios for equilibrium, at rest or constant velocity. So which paragraphs show either both constant velocity at rest or constant v and rest? So choice A shows a constant velocity and acceleration. B is constant velocity for both. That's actually our answer, but let's look at choices C and D just to make sure. C shows acceleration for both, and choice D shows acceleration and constant velocity. So our answer here is choice B. Excellent. Alright, number 10, Newton's third law. So here we have a student pulling a sled with a force of 20 newtons. We're looking for the force that the sled exerts on the student. So in response to the student pulling the sled exerts a force back on the student. So based on Newton's third law, action-reaction, equal in magnitude but opposite in direction. So here our answer should be also 20 newtons. Do not be fooled by these extra numbers. This is the tricky thing about Newton's laws problems, is all these words, they throw all this extra piece of information, but you have to focus on what the question is asking for. Alright. Here's a joke. What do you call a 3-humped camel? Pregnant! Alright, our final graph question for this part here is we're looking for what time interval of this graph shows the object at constant velocity. So if it's constant velocity, it's in equilibrium. That means our net force is 0 newtons. And so let's look at this graph and find that time interval where the graph reaches 0 newtons. And that is from time interval 3 to 4 seconds, choice C. Number 12. Here, this is an interesting one. So it's asking for the magnitude of the acceleration of block B. So here block B is lumped together with block A. And so when you push the force on block A, it pushes along block B as well. So because these two blocks are sort of mushed together, we treat them as one single piece of mass. And so their total mass now, you combine them together, is going to be 3 kilograms. And we still apply our net force of 12 newtons. And we solve for A, and we should get A is equal to 4 meters per second squared. Now let's get on to number 13. So this is an example of Newton's third law. A carpenter hits a nail with a hammer. Compared to the magnitude of the force the hammer exerts on the nail, the magnitude of the force the nail exerts on the hammer during contact is the same. Simple. If anything sounds like Newton's third law, I would just assume the force is the same. Remember, the force is the same. What's going to be different is the acceleration. Okay, number 14, which statement explains why a book resting on a table is in equilibrium. So, once again, equilibrium is balanced forces. And if we draw a free body diagram for a book on a table, the only two forces acting here is gravity of its weight pulling downward. And in response to that, the surface is going to exert what we call the normal force going back up. equal but opposite in direction, so these two forces balance out, causing it to be at rest and in equilibrium. So the only thing that shows that is statement D. Number 15, be careful, do not fall for the tricks. So it's asking for the mass of the spacecraft when it's outside the Earth, and it gives you its mass on the Earth. You should know that mass doesn't change here. The only thing that changes should be gravity, and so the weight will change based on the gravity of that new location. So if it's 2 times 10 to the 4 kilograms on Earth, then it should also be 2 times 10 to the 4th in space. Choice B. Alright. Let's go on to number 16. As an astronaut travels from the surface of Earth to a position that is 4 times as far away from the center of the Earth, the astronaut's either the mass or the weight. Okay. So here, once again, mass stays the same, but the weight is going to change. But by how much? So if we're going away from the Earth and into space, it's likely going to decrease. That's why astronauts feel weightless in space, because there's no gravity. So here, the only thing that fits that is choice B, mass remains the same. Now let's move on to 17 and 18. Alright, so these are where weight can be a little tricky, so it's knowing the difference between mass and weight. Here, they gave us the mass of the container of rock, 65 kilograms, and it tells us that the acceleration due to gravity on the moon is 1.62 meters per second squared. And they're asking us for just the weight of the container on the Earth's surface. So we're looking for weight, F of G. Our mass is still 65 kilograms, and this time we use the G value of 9.81 meters per second squared because now we're on Earth. We do not use the moon's G value. And you should get 638 newtons as your answer. Number 18, when a 12 newton horizontal force is applied to a box on a horizontal tabletop, the box remains at rest. The force of static friction acting on the box is, okay. So static friction is what causes objects to stay at rest until you apply a force that is equal or greater than that static friction. That's when the objects will start to move and overcome that static friction. And so here, if it stays at rest, no matter how hard you push, that means our static friction here is going to be greater. It's still a lot of static frictional force acting on this object. And so if we push with 12 newtons, that means our static friction has to be greater than 12 newtons. Choice B. Number 19. Now we're seeing a very interesting type of graph, how the mass changes as the distance increases over time away from the Earth. And so we should see that mass doesn't change no matter how far away from the Earth you are, so it's choice A. Number 20. Here we have a 4 kilogram object accelerating at 10 meters per second squared on a rough horizontal surface. So that means there's friction involved. So let's draw a free body diagram. We're pushing 50 newtons to the right, and we have friction acting to the left in response, and this unbalanced forces cause an acceleration of 10 meters per second squared. Okay, so when we have a mass and acceleration, we can figure out what's the net force, the overall net force acting on this object. Remember, net force is the overall amount acting on it. So we have our net force, 50 newtons, and force of friction. Take the difference of them to find our force of friction. But first we need to figure out net force with mass times acceleration. 4 times 10 should get us 40 newtons as our net force. So 40 newtons is the difference between the right side and the left side. So that should give us that F of F is equal to 10 newtons. And that's it. Alright, so numbers 21 and 22 wants us to use this part of the reference table where all the mu values are given for the materials given. Alright, number 21, here we have a car driving across different surfaces, and we're going to figure out which of these surfaces produce the greatest amount of force of friction to stop the car. And so we have to base it on the mu values, the coefficients of friction. And so the greater that mu value is, the greater the force of friction. And so looking at each of our four materials, we should see that 0.6A gives us dry concrete as our greatest force of friction for the surface. Number 22, we have an object, a rubber block, moving across a dry asphalt surface at a constant speed. So constant speeds are keywords to tell us that the force to the right is equal to the force of friction on the left. So the force of friction is our way to solve for F. And we find it by mu times the normal force. Because it's rubber on dry asphalt, our mu value will be 0.67. You look it over on the table over there. And our normal force is given as the weight of the object, 60 newtons. Okay? And so if you notice there, 60 newtons precedes the rubber block in that problem. So that typically describes the weight of the object. Sometimes they use mass to precede it, but this time they gave us immediately the weight of it. And if you know, weight and normal force are the same. So anyway, 60 newtons is our normal force times 0.67 our mu value, and you should get 40 newtons as your force of friction, which is equal to the force applied. Alright, now the last page. Alright, so we got this one scenario that deals with problems 23 to 26. We have a wooden box and a wooden floor, and we're looking for the magnitude of the frictional force on the box. So wood on wood gives us our mu value of 0.3. And we know to use kinetic because it's moving along already. If it were just starting to move, then that's when you use static. But since it's already in motion, we use the kinetic coefficient, that's 0.3, times the normal force, which is the same as the box's weight, 20 newtons. So 0.3 times 20 gives us our frictional force of 6 newtons. And that we carry over into the next problem, number 24. So we're looking for the net force. If we have 8 newtons acting to the right and friction acting to the left, 6 newtons, our net force is the difference here because they're in opposite directions, and we get 2 newtons as our net force. Now we carry that over to solve number 25. Well, actually that comes later. Number 25 asks us to find the mass of the box. This time we use the weight of the object to find that mass. Our weight is 20 newtons equals m times g. We solve for m where g is equal to 9.81 meters per second squared. By mistake I put kilograms, it should be meters per second squared. And our mass is approximately 2 kilograms. Now you carry all this over to find out our acceleration of the box. F net equals ma, 2 newtons is our net force. Our mass is approximately 2 kilograms. We solve for A, and A is approximately 1 meter per second squared. Alright, now the final set. Okay, number 27 deals with the coefficient of kinetic friction and how will it change if you change the forces applied in the problem. So here, if you notice, the coefficient of friction is based on the material of the two surfaces in contact. So as long as you don't change the material, no matter how much force you apply, then that coefficient should stay the same. So that should be choice C. Okay. Number 28. Jim wishes to push a 100 Newton wood crate across a wood floor. What is the minimum horizontal force that would be required to start the crate moving? So this is just like our lab, where we use the pulley system to figure out the coefficient of static friction. Okay, and so if we're looking for the minimum force, F, going to the right, we need to find out what that force of friction is going to the left, because in this scenario, these two forces are the same, left and right. And so we could start with looking at our vertical forces up and down. The force of gravity pulling down the weight is given to us as 100 newtons. And in response, the normal force is also 100 newtons, based on Newton's third law. So we use the force of friction equation, F of F equals mu times F of N. In the problem, they told us the material is a wood crate across a wood floor, so wood on wood is our material here. And now I just realized I made a mistake here. It's supposed to be the static coefficient, not the kinetic. I accidentally used 0.3 as our coefficient. It should be 0.42 since we're looking at the static scenario, not the kinetic. My mistake. So 0.42 times 100 newtons should give us 42 newtons, not choice A, 30 newtons. So the answer should be choice B, my mistake. Okay, now the final problem, number 29, we have a 0.5 kilogram frog. Exerts an acceleration of 3.0 meters per second squared, and we got to figure out the magnitude of the net force exerted by the legs to get that acceleration. And so here I'm going to show you the minimum amount of work you need to show to get full credit here. So first step, write the equation you're using, F net equals ma. Second step, you substitute everything in with units. Once again, units are important here. Number 3, you just solve it and you show the correct answer with correct new units. 1.5 newtons is our answer.